Kevin. So this week we have started solving some exercises about rational functions, and we are going to continue also next week by this lesson. So let us go for the important things that we have learned this week. So first of all, let us remember together that we have types of functions that are in the form of ax plus b over cx plus d. This form means we have first degree over first degree. In this function, we have the domain of definition is all the real numbers minus d over c. Also, it admits a derivative. And we have two asymptotes. The first one is vertical because we have in the denominator first degree. And the second one is horizontal because if you take the highest over the highest, you're going to have a over c as a horizontal asymptote. Let us take an example of this type of function. So we have function which is x minus 2 over 2x plus 2. The domain of definition, of course, you take the denominator different than 0, then you will have x different than minus 1. So the domain is minus infinity minus 1 plus infinity. So now the limit when x tends to minus infinity, you take the highest over the highest and you have 1 over 2. And x tends to plus infinity, also you take the highest over the highest and also you get 1 over 2. So y equals 1 over 2 is a horizontal aspect. Also, we have to find the limits when x tends to minus 1 minus and minus 1 plus. So we have when x tends to minus 1 minus plus infinity and when x tends to minus 1 plus minus infinity. Here plus infinity and here minus infinity. So we have x equals to minus 1 is a vertical asymptote. Now, after finding the limits, we need to, sorry, do the derivative and the sense of variation. So the derivative is u prime v over u prime v minus v prime u over v squared, which is 6 over 2x plus 2 squared. This is positive for every x. So it doesn't have any local extremum. Of course, it's not going to have any maximum or minimum because the derivative is positive for every x. So as you see in the table, we put first the domain, which is minus infinity minus 1 plus infinity minus 1 is blocked. And it's positive, so it's increasing all the way. Now, we still have to find the x-intercept and the y-intercept. So for x equals to 0, y equals to minus 1, and this is the y-intercept. For y equals to 0, x equals to 2, of course, you replace these points in the main function. So it's x equals to 2, which is the x-intercept. Now, when you want to draw the curve, the first thing you have to do is to draw the asymptotes. We have here two asymptotes, the vertical one and the horizontal one. The first part of the graph, it's increasing from half to plus infinity. And the second part of the graph, it's increasing from minus infinity to half asymptote, not half a point. And it passes through these two chords. So this is the first function. Now let us continue. Of course, I'm not going to solve all the cases of the functions. So now I'm going to go for the oblique asymptote. So we've already learned about the vertical asymptote and the horizontal asymptote. So now we're going to talk about the oblique asymptote, where we have an oblique asymptote. It's either on plus infinity or minus infinity. How do we prove that this equation is an oblique asymptote, or this straight line is an oblique asymptote? We have to do first f of x minus 5. And then we do the limit when x tends to plus infinity or minus infinity. Either way, I should get 0. If I get 0 as a result of the limit for the f of x minus y, then this line is an oblique asymptote. But how do I determine the oblique asymptote? If you want to determine the oblique asymptote, you have to do the long division. So we have the function minus x squared plus 5x plus 4 over x minus 2. You do the long division, and when you divide it, you will get minus x plus 3, which is the oblique, plus 10, this is the remainder, 10 over x minus 2. So the oblique asymptote is minus x plus t. So not every time they ask you to find the oblique asymptote. They give you the oblique and they ask you to prove that it's an oblique asymptote. But they ask you first to substitute this form of the function in this form, because this form is easier for you to find the oblique, to prove a center of symmetry. So this form is easier than dealing with this one. Now, after the oblique asymptote, we still have one more thing to learn, which is the relative position of the curve and the oblique. In order to know the relative position, when I say relative position, I mean which one is above, which one is below, and sometimes the curve is above, but later on it's below. So how do I do this? Actually, I do f of x minus y, okay, and I get this function, and I discuss this function according to the values. So we notice that if x is greater than 2, this form will be positive, which means that the curve is above the oblique. But when x is less than 2, this form is negative, then the curve is below the oblique. So that's how we study the relative position of the oblique and the curve. Of course, here you have a lot of examples that you can solve them, as you can see here. These are, we already learned them in the rational function. They are not new. The only new thing that we have learned in this lesson is the oblique asymptote. How do we find the oblique? How do we prove an oblique asymptote? And how we study the relative position of the curve and the oblique asymptote. Okay?